Okay, this lesson is 4.1 exponential functions, but I just wanted to let you know there are some interesting applications in this chapter. There's home mortgages, auto trade-in, depreciation, car loans, compound interest is one we'll take a look at today, and population growth. Okay, so 4.1 we're going to be talking about exponential functions. And they're called exponential functions because the variable itself is the exponent. All of these functions are one-to-one because they never share the x and the y, and they happen to always be increasing or decreasing throughout the domain. So they never repeat. You never have that same y value again. So they are one-to-one. So they have inverses. That's another thing. Example 1, what we want to do is take a look at f of x equals 2/5 raised to the x, and then we're also at the same time going to look at 5/2 raised to the x. And what you want to notice about this is that the base, the 2/5, that's the base, that's less than 1, and then the other one, the base is greater than 1. So there's certain things that happen when they're greater than 1 and less than 1. So first, whenever the a is greater than 1, you can just plug in your x values, of course, there and see what you get for the y values. And you notice that the one on the right here, a is greater than 1, it looks like it actually does what? Does it get bigger or smaller? So let's take a look. Let's start plotting some points. So when the a is actually bigger than 1, it's called exponential growth, and when the a is less than 1, it's called exponential decay. So you can see how I'm color coded. The 2/5 as the base is the one that actually gets a lot smaller over time as you keep raising x to positive exponents. And then the other one, the red one, is for growth, population growth, etc. Okay? They both go through the point 0, 1, you can tell, because if you plug in 0 as the exponent, of course the y value is 1 there. Okay? So what we'll do is we could, I'm not going to do it right now, but you could use a graphing calculator to graph the following functions. So we could do y equals 3 to the x, and see what we get. And what you'd find out is that the horizontal asymptote is equal to 0. And actually, I'll just do a rough sketch of what this would look like. It would look like this. It would, of course, go through 0, 1, and it would be roughly like this. Okay. And then if we did the next graph, the y equals 3 raised to the x minus 2, what that would do is that would shift the graph 2 units to the right. So it would be looking very similar, but it would just look like this. Shifted 2 units to the right. So it should have a point there. If I plugged in a 2, then I should have it turn out to be 1. So, instead of that point being 0, 1, now it's going to be 2, 1. Does that make any sense? And then the 3 to the x, so this is the blue one here. And the other one is the black one. That one. Okay, then the other one is just lowering the horizontal asymptote that used to be at y equals 0, and now it's going to be shifted down 2 units. So let's see, it used to go through right here, but now that's going to be shifted down 2 units, so it's actually going to go through right there. So it should look roughly like this. You can tell it's shifted down 2 units. And if I was a little wiser, I'd put it on the same graph. So let's say it would be something like this, roughly. Don't hold me to it, but something like that. If you do it on a graphing calculator, you'd be able to tell a little bit better. Okay? That just gives you an idea of the shifts. all of our same transformation stuff applies to exponential functions. Alright, next thing is let's look at an example where we're going to do a little solving. Okay, let's solve for x. And actually, I'll just use the animation. Okay, so I've got 3 raised to the 5x minus 8, and I really just want to solve for x. The technique on this is that you really want to get the bases to be the same. So you kind of notice that's a 3 and that's a 9. You pretty much are looking for some factor, that they both have. So 3 is that number. So try to make 9 so that it's 3 raised to a power. You notice that 9 is the same thing as 3 squared, so that works. And then kind of just do some algebra after that. So notice that we multiplied the powers here. So distributed actually, so that was 2x plus 4. That makes sense. And then now logic would say that, hey, look, the bases are the same, these are the same, so therefore the exponents have to be the same. So we just set the exponents equal to each other. And so 5x minus 8, so we're just focusing on the exponents. And we're setting those equal to each other, and then we just solve for x. So, of course, I added 8, and then divided by 3, so I got x equals 4. All right. Try a little harder one even. So that one looks pretty ugly. So what we want to do is we want to try to kind of make all of the bases the same. Unfortunately they seem to have some factors of 3 in there. So I rewrote it. This 9, turned into, first it was 3 squared, just to show a little work there. 3 squared, and then raised to the 2x. So it multiplied the powers, so that became 4x. And then this 1/3, that's actually 3 to the negative 1. If you brought that up to the top, you'd have to change the exponent. So that's how it became 3 to the negative 1. And then over here, of course, 27 is, 3 cubed, so that's nothing crazy. All right, next step. So now what we did is, well, the only thing I did over here is I kept the 3, and then it looks like just added the exponents. So when you're side by side like this, you keep the base, you add the exponents, so 3 minus 2x. Then over here, I distributed, because those were power to a power, so you multiply the exponents. All right, so next step, we keep the base. So again, they're side by side right here, so we keep the base and we add the exponents. So 4x minus x is 3x, and then minus the 2, and then on the right I didn't do anything yet. Now notice they're both 3 raised to a power, so the bases are exactly the same. So now we can set the exponents equal to each other like we did for the last problem. So we set the exponents equal, solve for x, so x equals 1. Alright, now we're going to try a different kind of problem. We're going to try to figure out what would the exponential function be if they give us a little information. We want to try to come up with the equation itself, or the function itself. So this has a little bit of a process to it. The horizontal asymptote that they give us, that we remember that that's what shifted it down. It used to have a horizontal asymptote of y equals 0, but now it looks like it's y equals negative 2. So that means that our c is actually negative 2. Again, because it shifts it down 2 units. All right. So the next thing we're going to do after that is we're going to use the x-intercept that they give us. So the x-intercept that they gave, get this tool out of the way. The x-intercept that they gave, actually using the y-intercept. So we're going to plug in a 0 for the x, and we're going to plug in a 16 for the y, and see if that helps us out a little bit. So notice when you plug in a 0 as the exponent, that becomes 1, so that's why that helps. This becomes 1, and then that's going to enable us to figure out what the b is. So then we solve for b, we're going to be able to tell that b equals 18. And then, so far, let's kind of see what we've got. So far, we've got this. We still don't have what the A is, so we've got to figure out what the A is. So I'm going to go to the next slide, so I have a little bit more space. And just rewrote it. And now what I'm going to use is the x-intercept. Because we know that when we plug in a 2, we're supposed to get a 0. So what we're going to do is we're going to plug in a 2 right there, we're going to plug in a 0 right there, and we're going to solve for the missing letter. The missing letter being A. So see the 2 we plugged in for the x, and the 0 we plugged in for the y. Now we're going to solve. So subtract the 2, and then divide by 18, and of course that's 1/9. And then we should be able to solve for A. You can do it a number of different ways, but one way you could do it is the way we were solving those other equations. So you can rewrite 1/9. 1/9 is actually 1/3 squared, and then we can pop that up to the top. Kind of noticing that that's a -2. It can be nice if that was a -2. So those would be the same. So this would be, that pops up as 3 to -2. Now it's kind of reverse logic. I mean, it's similar. The exponents are the same, so therefore logic would tell you that the bases have to be the same. So we would conclude, that A equals 3. Definitely. A equals 3. So we can use that, and now we've got all the pieces. So our final answer with all the pieces in there is that. All right. The last thing that we need to talk about is compound interest. So this is used a lot. If you go buy a car, they're going to use compound interest. Credit cards are going to have compound interest. If you invest money, most likely it's going to be with compound interest. So definitely used a lot. So let's talk about the pieces here. So P is always the principal. That's the starting amount that you borrowed or the starting amount that you put into an account. The N is the number of interest periods per year, however many times it compounds. If it compounds quarterly, then we would say 4 times a year, every quarter of the year. Let's see, yeah, that would be right. And then if they do it every semi-annually, then twice a year, monthly, 12 times a year, etc. Right? All right, T is always in the number of years, and then A is the total amount of money that it's going to accumulate after T years. All right, let's try a problem. So let's suppose we got $1,000. We invested at an interest rate of 9%, compounded monthly. So we get the number of times that compounds there per year. Find the new amount after 5 years, 10 years, and 15 years. So we're just going to do the same thing each time. We're just going to plug the numbers in. So let's do the 5 years first. So we plug in everything. You can see the 9% there. Need a different color so you can see it. Yeah. So we got the 9% right there. We got the 12 because again it's monthly. We got the N there again, and then we got the T for the number of years, and then we just do the math, right? Get your calculator out. That's fine, and we get total money is that. Okay, and then let's do the same thing for 10 years. And, the only difference there, plugging in 10 for the T. And then we get a lot more money. So that's good. Now 15 years. 15 years, we get that much money. So that's cool. And was the percent increase the same in each of the 5-year spans? So that's actually a good question. If you looked at, how much you gained in the first 5 years, the second 5 years, the next 5 years, is it basically the same thing? Does it really even matter if I leave it in there for 15 years or 20 years? Does it really make that big of a difference? Well, we have to go back and see what the gains that were made. So the first 5 years, we gained that much money, $568.68, because that was what the total, was 15, what was the total? 1565. And then the second 5 years, the difference between 1565 and 2451 was 885, so we gained a little more. And then the third 5 years, we went from 2451 all the way up to 3838. So that was more than a $1,300 increase during those 5 years. So we have a resounding no. And the reason for that is because this function is a good example of an exponential function. Because we have the 1,000, the 1,000's right here, and then we've got this is our base, it's like our a, and then we have our exponent. So this is a good exponential function. And so when we plot the points, we say, hey, at 0 years, we got $1,000. 5 years, we have a little increase, and then 10 years, a little increase. And we notice that's growing exponentially. And it makes sense because the one variable here that we're talking about, or that we're leaving as the variable, is time in years. So, good example. All right.